Okay, so let us continue with our discussion about covering spaces. So let me recall in the last lecture we looked at why the fiber over a point of the base space of the universal covering can be identified with the fundamental group based at that point. Okay, so we got a picture like this. So if x sub u and iv is the universal cover for the topological space X, okay, then I told you that given a point small x in capital X, then the fiber P inverse of X, namely the set of all points which are mapped to X under P, is canonically, which means naturally, bijective to the fundamental group of capital X based at small x. Okay, so in fact we had a statement for a general covering from which this followed. Okay, namely, if you had a general covering space, a covering map, if x tilde to x is a general covering map, then you take a point small x in capital X, then the fiber P inverse of X, I said, was it can be canonically identified with the coset space being the fundamental group of the space below at the base at the point below mod the image of the fundamental group above, where x tilde was a point that went to X. Okay, so each fiber looked like this coset space, and P lower star was the group homomorphism from the fundamental group above to the fundamental group below, fixing a base point above which goes to a base point below, and P lower star was an injective homomorphism. Therefore P lower star of the fundamental group above was a subgroup of the fundamental group below, and this coset space turned out to be canonically, that is naturally identifiable with the fiber. Okay, and as a special case, when x tilde is the universal covering, then you know that the for a universal covering the covering space is simply connected, so the fundamental group is trivial, and therefore this term goes away, this becomes just the identity subgroup, and you get this. Okay, so we got a picture like this, we got a picture in this form. So this was X, and this x tilde on this X, now in this case X, the universal cover over X was a space which was gotten by, for every point X I put a copy of the fundamental group based at small x. So you take some other point x prime, then I get the inverse image is the fundamental group at x prime. Okay, so in this way the universal covering space is just all these fundamental groups put together, okay, as at least as a set. Okay, and in other words we say that this mapping is a fibration with fiber isomorphic to the fundamental group below, and when I say fundamental group below, I don't worry about the base point, because X is an arcwise connected space, and the fundamental groups at two different points are isomorphic. Okay, so now so this explains why the fiber looks like the fundamental group, okay, below for a covering map that involves universal covering. Okay, we need to also look at another question. The other question is the following. So let me recall, so let me draw a line here. So let me recall again that we looked at these basic examples, started with a non-zero complex number and looked at the map from C to C mod the group of integer translations by this non-zero complex number, and this map gave this map was into a quotient, and this quotient inherited a Riemann surface structure, and so this was the Riemann surface structure C sub omega, Riemann surface structure on the cylinder. So this is Riemann surface structure on the cylinder, which is just which is homeomorphic to S1, the circle, cross R. Okay, and what we noted was that the first fundamental group of the cylinder, okay, and mind you, the first fundamental group has got nothing to do with the Riemann surface structure, it is just defined topologically. This first fundamental group is isomorphic to this group of translations by integer multiples of omega, which is a subgroup of automorphisms, holomorphic automorphisms of the covering space, which is C. Okay, this is the covering map, this is the universal covering because C is simply connected, and the fundamental group of the base is isomorphic to a subgroup of holomorphic automorphisms above. Okay, and similarly we had a similar situation for the torus. So in the case of the torus, complex torus, we fixed two complex numbers, and of course assume that they are linearly independent over R, so the ratio is not real. Okay, and we took the following map, namely going modulo the integer the translation by integer multiples of these two complex numbers. Okay, and this turned out to be a Riemann surface structure on the complex on the torus, on the topological torus, on the topological torus, which I just call it as T, which is homeomorphic to S1 cross S1. Okay, and of course this map is say pi sub omega 1 comma omega 2. This also is an example of a universal covering map, and again in this case we find that the fundamental group of the topological space below is isomorphic to the this group, which is just a subgroup of the holomorphic automorphisms of the universal curve. Okay, so so the question is the fundamental group of the base space in both cases can be identified as a subgroup of the automorphisms of the cover of the universal covering space. Okay, so why does this happen? We need to understand this. Okay, so that's what we are trying to now understand, and the way to do that, or at least one way to do that, is first to tell you how one can construct the universal covering space. Okay, so of course, so this argument will also help us to construct the universal covering space, and eventually it will also explain why the fundamental group of the base space can be nicely identified as the automorphisms, a subgroup of automorphisms of the universal covering space. Okay, so so if you so let's start. So construct, let us give the construction of the universal covering space. Okay. So as I have always told, we are assuming all our topological spaces to be so in particular X, for example, we are assuming that the topological spaces are all Hausdorff arcwise connected, locally arcwise connected, and locally simply connected. Okay, so that's a blanket assumption. So what is one going to do? So this is how we construct the universal covering space. So let me draw a diagram. So it's very clear that so if this is X, so I want this X, the universal covering. If you give me the point small x, what I need on top is a copy of the fundamental group of X based at X, at least if you look at this situation. Okay, so basically we want at least as a set we want the universal cover to satisfy this diagram, namely over each point you have a copy of the fundamental group below based at that point below. Okay, so it's very clear that over X I will have to put the fundamental group at X, but then if you take another point, let me say X prime, what is it that we are going to put on top? Okay, so the answer to that is the following. What one does is that one takes paths alpha from X to X prime. Such paths always do exist because X is arcwise connected. Okay, so I can take a path like this, and I can take the homotopy class of this path and put all those paths on top. So this is what is going to go to X prime, and you see if X prime is equal to X, what am I going to do? I am going to just put homotopy classes of paths starting at X and ending at X, and therefore I am going to get the fundamental group. Okay, so there is a nice simple definition of the universal covering space, at least to begin with as a set. It is going to be just the set of all paths starting at X. You have paths starting at X, and then you go modulo homotopy, fixed endpoint homotopy. Okay, so you know if alpha and alpha prime are two paths such that alpha can be deformed continuously to alpha prime, then they will give rise to the same point above in the fiber over X prime. And of course you know what X prime is. X prime is just alpha of 1, it will also be alpha prime of 1, it is the terminal point of alpha and alpha prime. And of course a beta which is not homotopic to alpha is going to give you a different point above. Okay, and so you can see that when X prime is X, I am going to simply get the fundamental group, copy of the fundamental group above X. Okay, so and what is this map going to be? So I have to define this covering map, something that I should verify that finally will turn out to be a covering map. Okay, and the map is just a very natural map from this set to this topological space, and this map is simply you give me a path alpha and I just send it to the endpoint of the path alpha. Okay, so so that corresponds to this diagram here. Okay, so a point above lying over a point below is just homotopy class of a path from X to that point below. Okay, fixed endpoint homotopy class, right. So this is my starting point. Now to begin with, first of all, if you go back to this diagram, you see that if I took any other point x prime, what I would get in the fiber P inverse of x prime was something that naturally looked like the fundamental group based at x prime, okay. So we need to check whether that is going to happen there. See, it is already happening for x because that is the way we started it, but it does not look that way from the definition, but one needs to do a little bit of work. So let me write this down. See, P inverse of x is certainly the fundamental group of x based at x, small x, there is no doubt about it, okay, because this is going to be paths starting at x and also ending at x because of this definition, okay. So these are going to be loops at x modulo fixed endpoint homotopy, so it is going to give me just the fundamental group. Now what about a point like x prime? What is P inverse of x prime? Why should this look like the fundamental group based at x prime, okay. Well, for that let's so why is this going to look like the fundamental group of capital X based at x prime? So to understand this, let me fix or choose an alpha in this, let me choose a point alpha here, alright. So this is in P inverse of x prime. What does it mean? It means that the endpoint of alpha is x prime, right. And what I am going to do, I am going to define a map, so define from P inverse of x to the fundamental group at x prime, okay. So this is how I am going to show that the fiber over x prime looks like a copy of the fundamental group over x prime. What I am going to do is, see, give me any beta here. I am just going to send it to let me look at my notes here so that I do not mess up the notation. Yes, so I will define a map L sub alpha, okay, and this L sub alpha is just beta going to I think beta inverse alpha, okay. So you see, try to understand this, I have fixed this alpha and given any beta, okay, I am going to take beta inverse alpha. That means I am going to go like this and then I am going to go back by alpha. That is going to give me a loop at x prime, and therefore its homotopy class is going to give me an element of the fundamental group based at x prime. Now the claim is that this is a bijective map, okay, the claim is that this is a bijective map, and therefore every fiber has been identified with the fundamental group based at the point below, provided you just choose one, the identification was based on choosing a point on the fiber, okay. So why is this map injective and surjective? We can see that very easily. L alpha is surjective because let me again draw another diagram here. So I have x prime, so here is x, this is the path alpha that I have chosen, that I have fixed, the homotopy class of alpha has been fixed, and I have to show that this is this is the image of this map. So if I start with an element here which is a loop based at x prime, okay, if omega is a loop based at x prime, so my omega is going to look like this. Omega is a loop based at x prime, okay, and well I have to find a beta such that beta inverse alpha is omega, okay, and that's so if you work it out, you can see that I will have to just take so beta inverse alpha is omega. What I need is a path, I need an element over the fiber of x prime which means by definition a path from x to x prime, okay. And what is that path from x to x prime? I am going to just take alpha followed by omega inverse. So alpha followed by omega inverse, let us try this. So alpha is a path from x to x prime and omega inverse is also a path from x to x prime to x prime. So if I compose them, if I concatenate them, I will certainly get a path from x to x prime, okay. And where does this go to? This goes to, by definition, it goes to, by this map, it goes to omega inverse, it goes to alpha omega inverse whole inverse times alpha, homotopy class of this. And if you write this down, alpha omega inverse whole inverse is omega inverse the whole inverse alpha inverse, and that is so this is going to be just omega inverse whole inverse alpha, and you can see that this is just going to be omega, okay, because alpha inverse alpha is going to be the alpha inverse followed by alpha is going to be homotopic to the constant path at x prime, and omega followed by omega inverse whole inverse is just omega concatenated with the constant path at x prime is just going to be omega, alright, because the constant path at x prime is the it is the unit element in the fundamental group there based at x prime. So so therefore it is surjective, okay. Then I need to tell you that this is also injective. L sub alpha is injective for if, so let us assume that L sub alpha of beta 1 is equal to L sub alpha of beta 2. Suppose I assume this, okay. So again I have a diagram like this, so let me draw another diagram here. So I have 2 points above, so this is so let me draw a line here. So this is above, this is in x tilde, I have 2 points beta 1 and beta 2, and these 2 points are lying over the point x prime, and what do each one of them correspond to? They correspond to homotopic the homotopy class of a path from x to x prime, namely, so this is the path, say this is the path beta 1, this is the path beta 2, okay. And I have assumed that L sub alpha beta 1 is L sub alpha beta 2, so this by definition means that beta 1 inverse alpha is equal to beta 2 inverse alpha, okay, which tells you that beta 1 inverse alpha is homotopic to beta 2 inverse alpha, and then you can operate on the right by alpha inverse, okay, and that will tell you that beta inverse is homotopic, beta 1 inverse is homotopic to beta 2 inverse, and that will tell you that beta 1 is homotopic to beta 2. So what all this will tell you is that it will just tell you that beta 1 is equal to beta 2, okay. So therefore it happens that the map L alpha is certainly a bijective map, and in a sense we are still in the same situation like this. The only thing is that the fiber over x prime does not directly look like the fundamental group based at x prime. You will have to it looks like that provided you fix a path from x to x prime, and now philosophically you can now see why this should happen is because you see if you give me a topological space and give me 2 points and give me fundamental groups at those points, the only way of saying that these two are isomorphic is by joining an arc. Once you join an arc, okay, then you get an isomorphism of this fundamental group with that fundamental group, okay, and so otherwise there is no way of connecting these two fundamental groups. So it is necessary to connect x and x prime by a path or an arc, and that we can do of course because x is path arcwise connected, and that is exactly what is happening here. All you need is a choice of a point here which is actually choosing an arc alpha from, or a path alpha from x to x prime. The moment you choose it, you are able to identify the fiber with the fundamental group based at x prime. Okay, so in some sense this is at least set theoretically it's commensurate with this diagram. Okay, but we need to do more things. We need to so what do we need to do? We need to make this into a topological space. So we have to tell what are the open sets here. Then we have to say that this map is a continuous map. Okay, then we have to say that this topological space satisfies all the conditions that we want of topological spaces to satisfy in, at least in our discussion. Namely, you have to say that this is arcwise connected, locally arcwise connected, locally simply connected. Okay, then we will have to tell that this is a covering map. We will have to prove that this is a covering map. Then we will also have to say that this space is simply connected. Once you do all this, then this becomes universal covering. Okay, so that's what I am going to do next, right? So so let me begin. Let me make the following immediate observation. So the first immediate observation is that this map P is certainly surjective because capital X is arcwise connected. Okay, so P is surjective as capital X is arcwise connected. Why? Because, well, you give me so here is X, give me any other point x prime, then there is certainly a path alpha which connects x to x prime. Okay, and then this homotopy equivalence class of this path alpha is an element of the set x sub univ which is mapped by P to x prime, which is just x prime is just alpha of 1, the endpoint of alpha. Okay, so it's very clear that the map is already surjective. I mean, I think you should have noticed that already. Okay, now I need to tell you about how to make this into a topological space. Okay, so so that's again how to make into a topological space. So it's done in a very obvious way. You see, so here is my this is my set above, which I am trying to turn into a topological space, and of course in a way in which this map P becomes continuous. So this map P is also to be thought of in this process. So I have, see, so suppose I start with a point, let's say alpha. Okay, so this point is going to lie above the point x prime, which is just alpha of 1, where alpha is a path from x to x prime. Okay, and what would you imagine as a neighborhood of alpha? You would imagine something like this. Okay, and you would expect that to go down to, you know, the covering map. A covering map has to be an open map because it's a local homeomorphism. Okay, so you would expect this to go down to something here. Okay, so so let me rub this off so that let me draw it like this. Okay, and let this be an open set U which contains alpha of 1. Alright, and then if this map is continuous, nearby points should go to nearby points. Okay, so what's a nearby point here? It's something that should go to a nearby point here, and if there is a nearby point here, you know, what I could do is that I could join this, if I can join this by a path beta, okay, from alpha of 1 to this point. Okay, then that will give me the point above, namely this point is going to be alpha followed by beta. Okay, and by continuity you want nearby points to go to nearby points. So based on this idea, we define an open neighbourhood of alpha in the following way, okay. So it's exactly as intuitive as you see in the diagram below. So what you do is take an open set containing the point alpha as, I will write it as a pair alpha comma u, where u is an open set in capital X containing alpha of 1, which is the point above which alpha is lying. And what is this? See, this should be all paths of that form, namely this is all these paths of the form alpha beta, where beta is a path from alpha 1 in U, okay. So beta is a path from alpha 1 in U, right. So what is happening is that so long as I can connect a point in U by a path from alpha 1 to that point, then I take alpha followed by that path and put it in this set above, okay. And it is very clear that I am trying to here I am trying to reach all from alpha 1 I am trying to reach nearby points, okay, and therefore the points I get above are going to be points close to alpha, okay, in a neighbourhood of alpha. So this is the intuitive way to define these open sets, and once you define these open sets like this, what happens? So what happens is they do not give you all the open sets, but they turn out to be basic open sets, namely they form a base for a topology. And what does that mean? That means that if you take finite unions of sets like this and then take arbitrary finite intersections of sets like this, sets like this, and then you take arbitrary unions, these are going to give you all the open sets, and sets of this form are certainly going to cover this whole set, okay. So let me write that down. Sets of the form alpha comma u form a base for a topology on X sub, okay. So why do they form a base? Well, number one, you see, if I take the path to be the constant path at X, okay, and I take the whole space, okay, then I will simply get every point in the universal in this universal set, okay. So if you take something like this, then you are going to get everything there. And the second thing is that if you take if you have two such sets, let us say alpha 1 u1 and alpha 2 u2, okay, if you have two such sets and you have a point common to this, say gamma, okay, then what happens is that this point gamma is contained, it belongs to the following set, namely it is going to belong to So it is just going to belong to gamma u1 intersection u2, which is going to be contained in this intersection. Okay, so this is what is going to happen. So what's happening is so I should put if here, if two sets of this form intersect, okay, then you take any point in the intersection, you can find again a set of this form containing that point which is in the intersection. So this is the property of that says that these sets are basic open sets. So sets form a basic open set, sets of certain type are said to form a base for the topology if you know you take two of them, or say even finitely many of them, and you take a point in the intersection, then you should be able to find again a set of the same type in that intersection, okay, for finite intersections. So I have done it for two intersections, and you can do it for more than two but finite intersections, okay. So with these two properties it is easy to check that you can take the topology on x sub unip as the topology given by open sets which are of the form, you know, arbitrary unions of finite intersections of sets of this type, okay. So let me write that down. I think maybe it is worthwhile to draw a diagram for this one. So you see you have so above you have 2 points, so you have two neighborhoods of alpha 1 and alpha 2. So here is alpha 1 and then you have a neighborhood which is this neighborhood is alpha 1 comma u1, and then I have another, so that is alpha 2 here, and this neighborhood is, so this is all in x unip, so this is alpha 2 u2, okay. And how does it look like below? So this alpha 1 corresponds to a point to a path from x to alpha 1 of 0, alpha 1 of 1, and there is this open set u1 that I have chosen as a neighborhood of this point, and then so this is alpha 1, and then you have another path alpha 2, okay, and I am going to have well the endpoint is going to be alpha 2 of 1, and this set is going to be just u2, okay. And you know, saying that there is a point in the intersection would mean that there is going to be some gamma here, so I should put a square bracket to signify homotopy equivalence class. So this is my gamma here, alright. So saying that gamma is in this as well as this is the same as saying that, you know, gamma is, by going by this definition, so gamma is also alpha 1 beta 1, okay, where beta 1 is a path from alpha of 1 and in u1, okay, and it is also equal to alpha 2 beta 2, where beta 2 is a path in u2 starting at alpha 2 of 1, okay. And saying that these two are the same, that these two homotopy equivalence classes are the same, would tell you that the endpoints of these paths is the same because it is fixed endpoint homotopy, and that would mean that the endpoints of these have to be in the intersection of u1 and u2. So the diagram does not really look like this, okay. So the diagram looks more like this. So let me write that, let me draw one more diagram. So the diagram would look like this. So you would have the diagram would actually look like this. The diagram below will actually look like this, namely the diagram for x, you are going to have x, you are going to have alpha 1, you are going to have alpha 2, and then at the endpoint of alpha 1 you are going to have a beta 1, and then you are going to have from the endpoint of alpha 2 you are going to have beta 2, and this alpha 1 followed by beta 1 is homotopic to alpha 2 followed by beta 2, which is what you can call as gamma if you want. Okay, so it means that this point is in the intersection of u1 and u2, all right. So this point is in u1 as well as in u2, so this diagram looks like this rather. So there is this common intersection, so u1 and u2 have to intersect, all right, and then if u1 and u2 intersect, then I can consider this set of this form. So this is a path which starts at x and ends at that point, which is the endpoint of beta 1 and beta 2, which is lying in u1 intersection u2, and u1 intersection u2 is a non-empty open neighborhood of that point. So you get this a set of this form, okay, and it's clear that a set of that this is certainly contained in this as well as that, okay. So this thing that's shaded here, maybe it will let me draw a slightly neater diagram. So so this is alpha 1, this is alpha 2, and say this is beta 1 and this one is beta 2, and this is u1 intersection u2, and if you want you can call gamma to be either alpha 1 followed by beta 1 or alpha 2 followed by beta 2 or anything homotopic to that, and take the equivalence clause, okay. So this is x of course, and this is u1 intersection u2, okay. So the moral of the story is that you get a topology on x, on this x sub univ. So x sub univ gets a topology by taking open sets to be arbitrary unions of finite intersections of sets of the form alpha comma u, okay. So that's how you make this into a topological space, but the idea is very similar, okay. You want to pick points close to in an open neighborhood of alpha. You just do that by picking points close to the endpoint of alpha, namely points in a neighborhood of the endpoint of alpha, okay. Now that you have topologized this, the first thing I need to tell you is that with this topology this map is at least continuous, okay. So the map P from x univ to x alpha going to, so its P of alpha is just alpha of 1, that's our map, okay, is continuous. And why is this continuous? That's again quite easy to verify as follows. So for I will have to just verify that that is continuous at each point, okay. So what I will do is I will start with the point and then I will take its image, I will take an open neighborhood of that point and take the inverse image of that open neighborhood and show it's open, okay. So in fact what I will have to do is I will have to check that the inverse images of open sets are open, okay. So what I do so let me do this for if u in X is open and say alpha is in P inverse of u, okay, alright. So then the set alpha comma u is also going to be in P inverse of u and contains alpha, okay. So so basically what is happening is that, you know, if you take an open set here u and you take an alpha above, okay, and so what do I have to do is I will have to show that P, if u is an open set below, I have to show P inverse u is open. So I will have to show that every point of P inverse u is an interior point, namely I have to show every point of P inverse u is surrounded by an open set which is contained in P inverse u, okay. So what I do is take a point of P inverse u, so that goes to a point here, namely this point is just the endpoint of alpha, and then you know that I have this whole neighborhood above, namely alpha comma u, which is an open set. Each of these are also open sets, the basic open sets are also open sets, okay, because they correspond to so when I say take the open sets to be arbitrary unions of finite intersections, so the finite intersection could be just one set, that is the intersection of a family which contains only one element, and the arbitrary union may be just union of a family which contains just one element. So each of these are also there in this collection, okay. So each of these are also open sets, and clearly if you take a set like this, then its image is going to go into U, okay. That will tell you that this is going to be in P inverse U, alright, and it contains the point alpha. So alpha is surrounded by an open set, an open neighborhood inside P inverse U, and that is true for every point in P inverse U. So P inverse U is open, so we have verified the inverse image of an open set is open, so therefore P is continuous, okay. So so that makes finally this into a topological space and this into a continuous map, okay. What we next need to do is to verify several properties of this topological space, namely we will have to show that it is you know Hausdorff, you have to show it's arcwise connected, you have to show it's locally arcwise connected, locally simply connected, and then you have to show it's also simply connected. You have to show that this map is a covering map, okay. So maybe I'll next go on to try and tell you why this map is I mean why this space is Hausdorff, okay, which is very important to begin with. So I'll try to explain that. So my next claim is that this space is Hausdorff. Okay, so how do I show that this is Hausdorff? Well, so what is the definition of a space being Hausdorff? You give me two distinct points, then I can separate them with disjoint open neighborhoods. So so here is my space above X sub univ, and I have 2 points, let us say alpha 1 and alpha 2, and they will lie above their endpoints in X. So here is X, the point I have fixed, and you know alpha 1 is a path to from X to alpha 1 of 1, which is the image of this point under P, and well then I have another path alpha 2 that will go into alpha 2 of 1, that will end at alpha 2 of 1, and that is the image of this entropy. Okay, and suppose alpha 1 and alpha 2, so there are two cases when alpha 1 and alpha 2 have different endpoints and when they have the same endpoint. So let's look at both the cases easily, I mean one by one. Case 1 is alpha 1 of 1 is not equal to alpha 2 of 1. Okay, this is a very easy case, and you see these are 2 points in X and X is Hausdorff, so there are 2 open sets, two open sets which an open set which contains this, an open set which contains that, and which do not intersect. Okay, so since X is Hausdorff, there exists U1 U2 open in X with alpha 1 of 1 in U1, alpha 2 of 1 is in U2, and U1 intersection U2 being empty. Okay, so namely the picture is going to look like this. So I have a U1 here, so this is U1, and I have a U2 here, this is U2. Then it is very clear that if I take this neighborhood above given by alpha 1 comma U1 and this neighborhood here above by alpha 2 comma U2, that these two neighborhoods don't intersect. Okay, so let me write that down. So then U1, so alpha 1 comma U1 intersection alpha 2 comma U2 are 2 open sets above, they are open neighborhoods of alpha homotopy class of alpha 1 and homotopy class of alpha 2 which do not intersect. Okay, so so I will have to go on to the next case, namely when which is slightly more trickier, the case when both of these lie over the same point. So alpha 1 of 1 is equal to alpha 2 of 1. Okay, so the situation is, the diagram is like this. What I have is I have 2 points alpha 1 above and alpha 2 above that lie over the same point below, which is alpha 1 of 1 is equal to alpha 2 of 1. Okay, and so alpha 1 is also a path like this and alpha 2 is also a path like this, and X is a starting point. Okay, so I have this situation. So then the question is, what do I do? So the point is that you see the space X, so this is in X tilde, this is in X sub U nib, okay, and both of these points are going to this point, which is the end point of alpha 1 as well as of alpha 2. The point, what we need to use now is the fact that X is locally simply connected. Okay, since X is locally simply connected, this every point of X has a simply connected neighborhood. Okay, so what you do is you choose U to be a simply connected neighborhood of the point of this endpoint, which is the same endpoint for alpha 1 and alpha 2, and the claim is that the corresponding sets above with the same U are going to be disjoint. Okay, choose, since, so let me write that down, since capital X is locally simply connected, there exists a simply connected neighborhood open set U containing alpha 1 of 1 which is equal to alpha 2 of 1. Okay, then we claim that the open sets alpha 1 comma U and alpha 2 comma U their intersection is empty. So these are going to be the separating open sets, okay. And the point is that well these are going to be two neighborhoods which are going to map homeomorphically onto U. Later on we will see that, okay. But for the moment the claim is that these two don't intersect, and the proof for that, so this is alpha 2, this is alpha sub 2, okay. So the proof for that makes use of the fact that U is simply connected. Namely, what you do is that you assume that there is an intersection, non-trivial intersection, so you get a point here, and then you get a contradiction to the fact that alpha 1 and alpha 2 are distinct points. So you see I am starting with alpha 1 not equal to alpha 2, that means alpha and alpha 2 are not homotopic, okay. So you can get this contradiction for if gamma is in the intersection alpha 1 U intersection alpha 2 U, what happens? What happens? So the situation is like this. Maybe I can again draw a diagram here. So I have so this is all happening in X. So I have X here, small x. So I have alpha 1, I have alpha 2, and this is a common endpoint for alpha 1 and alpha 2, and then U is a simply connected neighborhood, okay. And what have I assumed? I have assumed that gamma is both in this as well as that. So that means gamma is alpha 1 followed by a path beta 1 in U, okay. So there is path beta 1 in U starting at this endpoint and going to some point, and alpha 1 followed by beta 1 is gamma up to homotopy, and then similarly the same thing happens here. So there is another path beta 2, alpha 2 followed by beta 2 is also gamma up to homotopy, alright. Now you see this the fact that this U is simply connected will tell you that any closed path in U can be continuously shrunk to a point, okay. So what it will tell you is that it will tell you therefore that alpha 1 and alpha 2 are homotopic, and that means that the homotopy class of alpha 1 will be equal to the homotopy class of alpha 2, but that's not true, okay. So this can be easily seen. So let me see whether I can write that down easily. All I have to do is so alpha 1 followed by beta 1 is homotopic to alpha 2 followed by beta 2. So I can write, let me write that down. Alpha 1 followed by beta 1 is homotopic to alpha 2 followed by beta 2, and this homotopy class which we are calling as gamma, okay. And see now what I can do is that I can operate by beta 1 inverse on the right. So what I will get is I will get alpha 1 beta 1 inverse is going to be homotopic to alpha 2 beta 2 beta 1 inverse, okay. But you see beta 1 inverse, okay, beta 1 followed by beta 1 inverse. So let me call this point as x prime, alright. Then beta 1 inverse is going to be homotopy to the constant path at x prime, okay. So what I will get on this side is going to be just alpha 1 followed by the constant path at x prime, and that is the same as so I should keep writing homotopy, so which is the same as alpha 1, okay. And what I have on this side is alpha 2 followed by what is beta 2 followed by beta 1 inverse. So you see beta 2 followed by beta 1 inverse is a loop at x prime, so it is homotopy to the constant path at x prime because U is simply connected. So what is going to happen is that I am going to get C x here also I am going to get C x prime, okay, and that is homotopy to alpha 2. So the upshot of the story is that alpha 1 is equal to alpha 2 as homotopy up to homotopy, which is a contradiction. So this contradiction tells you that this intersection is indeed empty and therefore the Hausdorffness is proved. Okay, so in my next lecture let me try to give you the other properties of this topological space that make it into a universal covering for X. Okay, so I'll stop here.